Throughout computer science, the maxim garbage in, garbage out reminds us that we need to pay attention to the quality of the inputs when assessing the quality of the outputs. For machine learning, the quality of predictions output by our classifiers depends on inputting good training data. Our focus so far has been on specific algorithms that do a good job of turning data into a classifying rule. But any recipe for turning data into a rule is only part of any real-world machine learning problem. We can employ machine learning to help decide how to allocate security resources or where to build a new factory, but we need to keep the broader context in mind. After all, data about past security incidents might not have been collected uniformly, impacting the algorithm's perception of where security resources are needed. The way we define our loss function to trade off pollution concerns versus cost of transporting raw materials would affect where the learner recommends we put our factory. In this lesson, we're going to situate our use of a machine learning algorithm into this broader context. We're going to look at some of the pitfalls that you can encounter in that broader context when trying to bring machine learning algorithms to bear on real-life problems. We'll talk about a few ways that you can intervene to mitigate these pitfalls. We'll also see that some of the problems just don't have good remedies. In these cases, being able to recognize the pitfalls will help you steer clear of situations where things will go wrong. In the worst cases, machine learning might do more harm than good, and you might want to just pull the plug. Not every problem with machine learning can be solved with more machine learning. To be able to talk about what can go wrong in an application of machine learning, even if the machine learning algorithm itself is fine, we need to widen our view a bit. We need to see the whole pipeline. So far, we've scoped the machine learning problem as labeled data goes in, a machine learning algorithm of your choice processes that data, and a rule pops out. But the labeled instances come from someplace. There's a data collection process by which things that are in the world come to be captured in a particular data set used for training. And once the rule is learned, the goal in an application is to have that rule deployed in some context that impacts the world in some way. Finally, in many cases, we continue to collect data from the world, but now it's a world that has been changed in some way by the deployment of our previous rule. Each of these additional arrows provides additional opportunities for things to go wrong. Imagine you are a company that is building a machine learning-based system for responding to customer questions about transportation. For example, someone might ask, "What bus should I take to go from Warwick to Quincy?" You might record the incoming calls and hire people to translate the audio into text. Once you've collected enough text data correctly matched with audio, you could train a machine learning system to create a rule that recognizes names of cities based on the audio signal. The data is raw speech, so you might choose a neural network as your classifier because they have proven particularly adept at interpreting low-level sensory information. So you run your raw speech data through your neural network and you train it up well. Then you'd install the recognizer in your phone-based system and it will be automated. Success! After it's up and running, you continue to record calls so that you can identify problems and improve your system. That's very responsible of you. What could go wrong? Well, it turns out that people in Quincy call their town Quincy. When they say Warwick, if they say it at all, they say Warwick. However, people in Warwick call their town Warwick, and they call the other town Quitzy. Now, Quincy has a bigger population than Warwick, and it's close to a major population center, Boston, Massachusetts. So there are likely to be a lot more examples of the Quincy accent than the Warwick accent in the initial data. And that's not bad in and of itself. But machine learning systems, being imperfect, have to make trade-offs. Your learning system will work hard to get the common cases right so as to reduce the overall error on the training set. That's what your loss told you it wanted. If you're lucky, the learner will get all of these cases right. But if it has to make a trade-off, it will do so in favor of the Quincy people. That's true even if it means the Warwick people's speech is recognized less well. If you deploy a system that is very reliable for people from Quincy, but error-prone for people from Warwick, who do you suppose will use your system regularly? Probably the Quincy people. If the system is frustrating enough, the Warwick people will gravitate to alternative ways of getting information. And that means when you recollect data, it will be biased even more heavily in favor of the Quincy people. The next time you train your machine learning system, it will work even harder to get the Quincy people right, and it will even try less strenuously to get the dwindling number of Warwick people right. Over time, your system will essentially be discriminating against the unfortunate folks from Warwick. They will be getting systematically poorer performance than the Quinceyites. Okay, this particular example is somewhat fanciful, but this kind of discrimination is no joke. Recognition accuracy can end up being distributed unfairly across subgroups. For example, there are well-documented cases of facial recognition systems working considerably less well for women of color, likely in part because they appeared too little in the training data. Improving performance in these cases can turn into a matter of social justice. Often, it is possible to remedy these issues by paying closer attention to the data used to train the system. In the Warwick-Quincy scenario, you might make sure to include a feature for where the caller is based. Quincy and Warwick have different area codes, so you could use the caller's area code to identify the two groups. Then you could train separate classifiers for the two regions based on this specific input feature. That way, the representational resources for the two groups wouldn't be in direct conflict. It's no longer the case that the system is getting the Warwick people wrong because it is trying so hard to get the Quincy people right. Throughout the field of data science, some of the most surprising and insidious pitfalls reside in the data collection part of the pipeline. But with machine learning, it's also more than that. If there is a tendency in the data, your machine learner may not only notice the tendency, it may also accentuate the tendency beyond what actually existed in the training data. I'll use a powerful machine learning system to demonstrate how easy it is for a machine learner to overvalue a trend it finds in the data. In 2019, an organization called OpenAI released one of the most powerful language models ever trained. Formally, a language model is an allocation of probabilities to sequences of words. In practice, that means we can query a language model with a partial sentence and ask how likely various completions of that sentence are. A language model can be used to help speech recognition or optical character recognition by bringing to bear top-down constraints on what things are more likely to be said than others. It can also be used for autocompletion or even text generation. The Allen Institute for AI created a web interface for the OpenAI language model. I accessed it on their website, and I prompted it with two different sentences. When the child was finished playing with the truck, and when the child was finished playing with the doll, the system predicted that it was twice as likely for a male pronoun to follow truck, 15.25% versus 7.6%. It was also slightly more likely for a female pronoun to follow doll, 14% versus 13%. In a sense, the machine learning system has internalized some gender stereotypes. It makes some sense, given that it was trained on real-world text, and the real world often has some pretty strong gender stereotypes. Training on data with unwanted stereotypes is always potentially problematic, but it gets more worrisome when we think about the influence of stereotypes on critical decisions such as hiring. The OpenAI system is much more likely to use a male pronoun for doctor and a female pronoun for nurse. When I asked it to complete, "I will only hire a doctor who knows how to use," it assigns a probability of 7.4% to his and less than 2% to her. Substituting nurse for doctor in the sentence brings the probability of her up to 12.1%, and his drops below 2.1%. Consider how we might use a language model as a way of assessing job applications. We might ask, what probability would you assign to this application, as a stand-in for whether it seems like the applicant would be a good fit for the opening? The extent that the model hasn't been exposed to certain groups in certain jobs, it's going to assign applicants from those groups lower probability. They will look like bad fits for the job simply because the system hasn't been exposed to those combinations. In this case, you could argue that we're just using the wrong tool for the wrong job. Language models aren't well formulated for assessing resumes. But in October 2018, Reuters reported that Amazon had explicitly tried to make a resume assessment tool based on machine learning. And try as they might, they couldn't get it to give women a fair shake for technical jobs. Their trained system rated applicants as less appropriate if their resumes showed that they had attended specific all-women schools, for example. The issue here is that the data that was collected wasn't suited to the task it was to be used for. Given past data of resumes and hires, a machine learning system is trying to match the decisions made in the past. And if past decisions have been biased away from women, then the system will learn to bias its decision away from women as well. It's what it was trained to do. Reuters reported that the software didn't like women, but that's unfair. The designers had wanted to interpret the output of the system as indicated whether they should hire, but what it was actually trained to guess was who they would hire. In this instance, the team was unable to find a way to debias the output and gave up the project. Many similar failures have been reported, and I'm sure there are many we'll never hear about. It's a hard problem to jump from past data to advice about how to decide in the future. In a related example, a team at Microsoft Research looked at word embeddings. These are systems that represent the meanings of words by locating them in high-dimensional vector spaces. Each word is assigned a point in space so that words that are used similarly are assigned similar locations in the space. Typically, these systems use hundreds of dimensions, which is very difficult to visualize, but conceptually, we have something like this two-dimensional rendition. People have observed an amazing fact. Systems trained this way tended to learn certain kinds of concepts as directions in the high-dimensional space. For example, the direction from the position of actor to the position of actress is similar to the one from him to her or from brother to sister. You can think of this direction as being the male to female direction. Pretty cool that the system discovers the idea of gender, especially since maleness and femaleness are not explicit features in the training data. The learning system is just trying to predict patterns of word usage. We can make use of these implicitly discovered concepts to solve an analogy problem like king is to queen as aviator is to what? The embedding has a very good chance of proposing aviatrix as the point that completes the parallelogram. But the machine learning algorithm can't quite tell the difference between definitional male to female shifts, like bachelor to bachelorette, and statistical male to female shifts, like truck to doll or doctor to nurse. For example, if we move in the male-female direction from carpentry, we get to sewing. If we move in the male to female direction from chuckle, we get to giggle. If we move in the male-female direction from brilliant, we get to lovely. These examples don't reflect the formal meanings of the words. They capture stereotyped patterns of usage. The Microsoft team showed that they can reduce this bias without doing too much damage to the overall embedding. They proposed the following steps. Figure out the high-dimensional direction that encodes gender. To do so, they identified 10 gender-paired difference vectors. They identified the main direction of difference using a machine learning and statistical technique called principal component analysis, or PCA. PCA is an unsupervised method that makes use of similarities between instances. It leverages computational techniques from linear algebra to re-represent its input data in terms of a lower dimensional set of underlying directions in the data. The smaller set of dimensions are known as the principal components, which is where PCA gets its name. The principal components themselves are sorted by importance, so dimension 1 is the best single-dimensional reconstruction of the data. In the case of pairs of gendered words, that single best direction ends up being gender. Then, for any pair of words that should not have a difference, they did a high-dimensional projection of those words so that they no longer differed in the gender direction while leaving all other dimensions unchanged. In this low-dimensional visualization, that would mean collapsing carpentry and sewing to a single point, and collapsing brilliant and lovely to a single point. But keep in mind that these points are embedded in hundreds of dimensions. It's like we're looking down on 2 points that are at different depths. If we rotate our view to another perspective, we can see that they remain distinct in many other ways. They just have no distinction in a particular direction that corresponds to gender. Geometry is where the problem showed up, and geometry is the tool that was used to solve it. Of the handful of different pitfalls that have been identified, this is the one that has the most comprehensive solution. Another subtle pitfall that is particularly difficult to remove comes up when we are trying to use historical data to change how we will behave in the future. Historical data has baked into it the way we have behaved in the past, and that can send misleading signals. Machine learning researcher Rich Caruana described a compelling case in which hospital information was used to predict patient outcomes. He wanted to use a machine learning approach to assess patients coming into a hospital to see which were at risk for pneumonia. If a patient is predicted to be at high risk for pneumonia, the doctors can allocate more resources to these patients to help make sure they survive their stay. All good, right? The team creating the system did everything by the book. They collected data on patients as they entered the hospital, they recorded age, medical history, vital signs, etc. Then when the patient was discharged, the team recorded whether the patient had suffered from pneumonia. The team used this data to train a highly accurate neural network classifier, and indeed, it did an excellent job with its prediction. But the doctors and machine learning researchers on the project balked at putting the system into practice. Turned out that their concerns were well-founded. They weren't sure what the neural network was doing, so they also trained a method called logistic regression on the same data. Logistic regression wasn't performing quite as well as the neural network, but the team could more easily tell what logistic regression was doing. And what the more transparent method of logistic regression was doing was odd. When assessing a new patient, it would rate someone with asthma as being low risk of pneumonia. When the doctors saw that, they were very perplexed. They know that people suffering from asthma are very prone to pneumonia. Why would the machine learner believe the opposite? Again, it's precisely because the doctors know that people suffering from asthma are very prone to pneumonia. The doctors treat patients with asthma very carefully and are tuned in to early warning signs that indicate that pneumonia might be taking hold. So the machine learners were not finding that people with asthma are, in general, less likely to have trouble with pneumonia. They were finding that people with asthma are less likely to have trouble with pneumonia when treated by doctors who know they have asthma. And of course, the learner was correct in this more narrow sense. But the output of the learner should not be used to change hospital policy. Taken at face value, the results suggest not treating asthma patients with particular care. The hero in this story is logistic regression. Well, the hero is Rich Caruana, who figured out what was going on, but the machine learning tool he used to do it was logistic regression. It's worth taking a closer look at this algorithm. I wish I had the asthma pneumonia data, but I did find another data set that has some interesting parallels. It's a standard data set from a tragic maritime disaster, a shipwreck, and we can look at the data to see what lessons it contains. Let's pretend we are safety engineers and we want to put measures into place to help prevent fatalities. It would be useful for us to be able to predict who is at risk of dying in the event of a shipboard accident. If we can figure out who is at risk, we could perhaps train the at-risk people on safety measures or place them on the ship close to trained personnel, something to give them a better chance at surviving. So we take historical data, run a machine learner on it, and use the learn rule to figure out who is at risk. Let's see what we get. We read in the training data ship.csv. We'll convert the file one line at a time into a numerical Python array. The resulting features are P-class, the passenger's class. It can be 1, 2, 3 for first class, second class, or third class. Sex, we code male as 0 and female as 1. Age, sibsp, the number of siblings and spouses the passenger has on board. Parch, the number of parents and children the passenger has on board. Fare, how much the passenger paid for the ticket. Embarked S, did the passenger get on the ship at port S? Embarked C, did the passenger get on the ship at port C? Embarked Q, did the passenger get on the ship at port Q? We randomly split the labeled passengers into training and testing sets. We train a neural network to predict who will survive. It gets a respectable error rate of 17%. But something is not quite right. I went through all the data and asked the model to predict the probability of survivor for each passenger. On average, passengers are 44% more likely to survive if they are female. In fact, for 100% of the passengers, their predicted chance of survival is higher as a female than as a male. From a policy standpoint, it sounds like the right thing to do is invest in protecting the men. The women seem to be fending for themselves quite well. But it's almost certainly a misleading result. We can't tell from this data whether women or men are better at surviving a shipwreck, all things being equal, because we know that things were not equal. The name of the ship involved in the accident we're studying is the Titanic, which struck an iceberg and sank in the chilly waters off the coast of Canada in 1912. The staff of the Titanic were told to put women and children first onto the lifeboats. So what we're seeing here is not useful for creating a new policy, because what we're seeing are the results of a prior policy used when the data was generated. The pattern of male-female results we're seeing is analogous to what researchers saw in the asthma pneumonia example. We can see these effects more clearly by applying logistic regression, just like Rich Caruana did in the asthma pneumonia data. I ran logistic regression, which is available as part of scikit-learn. It gets about an 18% error rate on the Titanic survivors data, which is only a bit worse than what we saw from the neural network. More importantly, the way logistic regression works makes it a lot easier to interpret the machine learning result. Logistic regression learns one weight for each feature in the data, So in this sense, it is very similar to the perceptron or a linear support vector machine. Even more so, logistic regression can be described as a special type of neural network. Logistic regression is kind of like a one-layer neural network with a sigmoid activation function. Actually, that's exactly what it is. It has one weight per input feature, and output activations are computed by taking the weighted sum and transforming it with the sigmoid function. Because of this specialized structure, the weights in logistic regression can be found somewhat more efficiently than training the equivalent neural network. I once attended a talk by a prominent statistician addressing a workshop of machine learning researchers. He said that he had to give credit to machine learning people. Specifically, he thought we were much better than statisticians at naming things. He gave a bunch of examples and pointed out that neural network is just a much more exciting name than logistic regression. Now, of course, machine learning folks would not agree that machine learning is just statistics with better names. I mean, for one thing, neural network refers to a far richer class of models than just the logistic regression model we're talking about now. And since it's better to call a shovel, we'll refer to this model by its more specific name, logistic regression. So, in what sense is logistic regression better than other neural network models in this situation? It's because of the way that the logistic regression model works. The model takes each feature in the input and weights it. Then, it sums the weighted features and applies the sigmoid to the result. The sigmoid transforms the total into something in the range 0 to 1, like a probability. The higher the weight that's on a feature, the more that feature contributes to pushing the probability towards 1. And that means we can directly interpret the feature weights. Positive weights are evidence for the positive class, and negative weights are evidence against the positive class. If we output the learned feature values in the Titanic data, what we see is that the feature with the most impact on survival is sex, and it's a big boost toward survival when the feature value is 1, female as it turns out. There's also a significant negative impact of passenger class. The first class passengers had the highest chance of survival, then things fell rapidly for people in second and third class. Here, we have a signal that should be important for the design of future safety systems. Third-class passengers had to travel a long, complicated route to reach the lifeboats, and many lifeboats had already launched by the time the passengers arrived. In addition, it's believed that the third-class passengers, unlike first class, were traveling with all of their worldly possessions and were more reluctant to abandon ship. There's a somewhat strong influence of number of siblings plus spouse in the negative direction, and there's an even stronger positive influence of people departing from Queenstown. Titanic expert might disagree, but my guess is that Queenstown Q was more affluent than Southampton S, and what we're really seeing is a proxy for passenger class. Regardless, the takeaway here is that some machine learning methods, like logistic regression, provide a much better window into how the learner makes decisions. Other machine learning methods, like more general neural networks, are much more opaque. An advantage of transparent methods is that there's a better chance we can tell that they have problems before they are deployed. Now, it's not entirely clear what to do when the data lacks the necessary perspective to be able to tell us how to intervene to help save more people. In a later lesson, we will talk about causal inference in machine learning. The causal perspective may provide just the right tools for drawing conclusions from this kind of confounded data that mixes data collection policies with differences in outcomes. Arguably, what we're seeing here is an example of the number one biggest factor that lies behind failures of machine learning. It is due to the use of an inappropriate proxy measure. A proxy refers to a substitute. We often train our models to predict one quantity when we really want to measure another. The proxy measure is the one we have. As long as our proxy measure is well aligned with what we really want, the results can have validity. Consider zip code and income level. These two features are not the same, but zip code is a proxy for other information that correlates extremely well with income level. People tend to live near other people with similar incomes. So zip code can serve as an effective proxy measure of income, and race for that matter. A well-studied example of a poor proxy measure comes up in predictive policing. If we could train a classifier to tell us where crime is likely to occur, we could deploy security officers to those areas in a more targeted way, reducing the overall cost of protecting the community. But we don't have a way to detect when crime happens, so we can't train a classifier using this information. But we could use arrest as a proxy for crime. That's something for which there is data, and surely there's some connection between arrests and crime, right? Sure, but the two are better aligned in some communities than others. Moreover, if the police force is already deployed in a low-income community, it is more likely to make arrests in that community independent of the actual distribution of crimes. If we train a model to predict where arrests occur, it will end up predicting that arrests are more likely where there are more police officers. If we then take arrests as a proxy for crime, these predictions suggest that we assign more police officers to wherever they were already patrolling. Just like the Warwick-Quincy case, initial imbalance leads to even worse imbalances. It's a positive feedback cycle, but acceleration of this positive feedback cycle is not evidence that real progress is being made in preventing crime. To sum up, the technical part of machine learning is concerned with turning labeled instances into prediction rules. But when we apply machine learning to real-world problems, we have to pay attention to the broader context in which data is collected and used, including how new data comes in after the system has been deployed. Like in the predictive policing setting, we need to make sure that the quantity being predicted, arrests, is a good proxy for the quantity we want to reduce, crime. If it's not, we should seek out better data that measures the quantity of interest more directly. We need to make sure that policies employed when data is collected don't obscure how predictions will change if a new policy is adopted. To avoid the problem of asthma patients looking like they are at very low risk for pneumonia, it can help to collect data in a more controlled setting. For instance, we could record precisely how doctors are treating the different patients and try to treat some of the non-asthma patients in similar ways to the asthma patients so direct comparisons can be made. We need to make sure that the loss function we use doesn't encourage the machine learning approach to ignore minority subgroups, such as the accent of people from Warwick or the faces of African American women. When that happens, we can consider alternate loss functions that more evenly weight errors across the classes. We can also try to proactively collect more balanced data. In some cases, like Amazon's attempt at creating an automated resume screening program, the machine learner is hopelessly biased. In these cases, we should give up. Machine learning makes it all too easy to deploy a plausible but damaging system, and harms are especially acute for smaller and more vulnerable populations. Whenever we use machine learning algorithms to solve real-world problems, knowing how to cast a skeptical eye on the results we're getting can help prevent their misuse. Machine learning is a powerful tool, but it's up to all of us to demand that machine learning is deployed in ways that minimize possible harm, even while society reaps the benefits.